Hello students, this is Dr. Savitha, Associate Professor, Department of Chemistry from Maharani Science College for Women, Mysore. In this video, we'll be learning what are aldehydes and ketone and its nomenclature. So, as we all know, aldehydes and ketones contain the carbonyl group. So, what is a carbonyl group? So, a carbonyl group is the one where the carbon is double bonded with the oxygen, and this whole unit we call it to be a carbonyl group. So, aldehydes and ketone contain this carbonyl group. And depending on the nature of the substance, the carbonyl group can be classified into aldehydes and ketone. So the unit carbonyl group, when they are present, we call them to be a carbonyl compounds. So in a carbonyl compound, when the two valencies out of which one is satisfied with an hydrogen atom, or a carbon is bonded to an hydrogen atom and another is bonded to an alkyl or an aride, then we call those group of carbonyl compounds to be an aldehyde. And when we take the other group of carbonyl compound, the ketone, here the carbon which is bonded to the oxygen is satisfied by an alkyl or an aryl group, and here we do not have any hydrogen atom. And the simplest example for an aldehyde is the formaldehyde, and it is the only one aldehyde without any alkyl group attached to the carbonyl carbon. And the other example for the aldehyde is the acetaldehyde, where one of the valency is satisfied by an alkyl, that is the methyl group, and this is an example for an aldehyde. So all other aldehydes such as acetaldehyde have one alkyl group and one hydrogen atom attached to the carbonyl carbon. So a few examples for aldehyde can be a formaldehyde where we do not have any alkyl or an aryl group and the valency is satisfied by only the hydrogen atom. Acetaldehyde or the propanoldehyde, or when we have an aromatic ring, that is the benzaldehyde. So these are a few examples for the aldehydes. Coming to the ketones, so when we take the ketone, the two valency of the carbonyl carbon is satisfied by an alkyl group, then we call those groups to be the ketone. The two alkyl group can be same, then we designate them to be the simple ketone. An example for a simple ketone is dimethyl acetone, ketone commonly called as acetone. On the other hand, it is not necessary the two alkyl groups should be the same, then we call it to be a mixed ketone. Ketone, for example, in methyl ethyl ketone, we have one alkyl group to be a methyl and another alkyl group to be ethyl. Apart from that, it's not always necessary to be having the alkyl group. One of the valency can be satisfied with an aryl, and an example is acetophenone or it is methylphenyl ketone. So when I compare the aldehydes and ketones, the aldehydes are more reactive compared to the ketone. The reason being the aldehydes have been attached to the hydrogen atom. Coming to the nature of the carbonyl compounds, that is aldehydes and ketones are electrophile. So, when we take the carbon bonded with the double bond oxygen, as we all know, oxygen is more electronegative than the carbon, and as a result, the carbon gets a partial positive and the oxygen gets a partial negative charge. Because of this, a polar bond is created. Because of the presence of the electrons which are on the oxygen, it is a partially negative, and efficiency it is a partially positive. So the partial positive carbon is an electron acceptor, that is an electrophile. So the nucleophiles like CH3MgP or ammonia will readily add to the carbonyl group of aldehydes and ketone. Coming to the nature of the bonding, as we all know, the carbonyl group is sp2 hybridization, and because of more electronegativity, the electrons are drawn more towards the oxygen, making the oxygen to be partial negative and the carbon to be a partial positive. As a result, during an addition or a condensation reaction, a nucleophile attacks this electrophilic carbon atom, and we get an intermediate product where the valency has been satisfied, and we get the hybridization to be the sp3 hybridization, and commonly this is called a tetrahedral alkoxide, an intermediate during the addition reaction or a condensation reaction. So what happens? The pi bond breaks and a nucleophile is added to the electrophilic carbon, making this to be a tetravalent, and it's commonly referred as tetrahedral alkoxide ion. Coming to the nomenclature, the generally aldehydes have a trivial system of nomenclature. So, according to this system, a common system of nomenclature of aldehyde, these aldehydes are named from the common names of the corresponding carboxylic acid. So when we take the methanoic acid, the IPAC name, the common name is the formic acid. So in the common nomenclature of an aldehyde, the ic acid is replaced with an aldehyde, and it is called as formaldehyde. Likewise, the acetic acid, the acid has been replaced by aldehyde, and it is called as acetaldehyde. It's also true with the other acid, propionic, butyric, valeric, boric acid, where correspondingly we add the term aldehyde and refer to be propanoldehyde, butyroldehyde, valeraldehyde, caproldehyde. So whenever we have a substituent, the position or the location of the substituents are usually referred by the Greek letters, which can be alpha, beta, gamma, and so on. So when we give the Greek letter, the functional group, the carbon atom adjacent to the functional group is designated as alpha, and the next we designate as beta, and the next carbon atom we designate as gamma. So for example, when I take here, this is the functional carbonyl oxygen, and the next carbon atom we designate alpha, and on the next to be the beta. On the beta, we have a substituent, the bromo, so we call this to be beta bromo butyryl aldehyde. The same is also repeated here, where we have a hydroxy group at the gamma, and hence we call gamma hydroxy valeraldehyde, and here we have a phenyl group attached to the alpha carbon atom, so we call it by the name alpha phenyl acetaldehyde. Coming to the nomenclature, according to the IPX system, the rules that has to be followed for naming an aldehyde are as follows. The longest chain containing the carbonyl group is first identified. The total number of carbon atom in the chain is counted. Then the aldehyde is named as the derivative of the corresponding hydrocarbon. For example, here we have 1, 2, 3, 4. So we have 4 carbon atoms. So the parent hydrocarbon will be the butane. So if I have a 5, I call it to be a pentane, and 6 hexane, so on. Then we are going to replace the E from the parent alkane to Al, and the name will be butanol, and the numbering will be given to the chain, so the functional group gets the least number, and we apply all other nomenclature rules, and we give the nomenclature according to the IPX system. So here we have 1, 2, 3, 4. So the parent name will be butane, and E is going to be replaced by Al. Apart from that, we have additional substituent on the second and third, and they are methyl. So we add them as a prefix, and we name this compound to be 2,3-dimethyl butanol. So it's once again a repetition of IPAC nomenclature. So in the trivial, we call this to be a propanoldehyde. Here we call to be propanol, and the other examples according to the IPAC nomenclature of aldehydes. So just to repeat, here we are replacing E with Al, and we call them to be alkanols for the aldehydes. And the order of priority basis, these are the functional groups. So aldehydes are here. When the aldehydes are above, then we add oxo for both aldehydes and ketones. Coming to the next, the ketones are also have the general nomenclature or a trivial nomenclature, where we just look at the alkyl and aryl groups and are arrange them in the order of alphabetical order and just add the suffix ketone. For example, here we have two alkyl groups. One is methyl and other is ethyl. According to the alphabetical, it is ethyl, methyl, ketone. Similarly, these are a few examples, and the common name for the ketones can be the acetone, acetophenone, benzophenone, or when we have additional functional group, it can be a salicylic aldehyde or cinnamaldehyde. Coming to the ketone nomenclature, the IPF rules are the same. Here, we are replacing the E with the ONA. For example, here we take the parent carbon. So we count the number of the carbon atom. Here we have 4 carbon atom, and hence the parent name will be the butane. So E will be replaced with the ONA. And next, when we give the numbering, according to the IPR rules, the numbering will be given so that the functional group gets the least number. So we start giving the number from this side. So carbon atom number 1, and the functional group will be getting the number 2, the next 3, and the next the 4. So we locate the position of the functional group with the numerical number. That is, we have the functional group attached to the second carbon atom, and hence it is 2-butane. Then we have additional substituent, that is, at the third carbon atom we have a methyl, which will be added as a prefix, and hence the name of this ketone according to the IPR nomenclature will be 3-methyl-2-butanol. The another example is the same here. So we have 4 carbon atom, the parent name will be the butanol, and since the functional group is on the second, we call it to be the 2-butanol. Then we look at the other substituents. We have a substituent on the third carbon atom and on the fourth. On the third, we have a methyl, so we add it as a prefix 3-methyl, and we have a hydroxyl group attached to the fourth carbon atom. So we call this ketone to be 4-hydroxymethyl-2-butanol. So the other examples are 2-butanol and 4-bromone, 4-methyl-2-butanol. This is all about the nomenclature of aldehydes and ketone. Thank you.